I'd like to thank the IAF faculty and staff for their constant support and attention since the first days and even before of my stay at the Institute. Special thanks to Professor McPherson for sending me in advance a personal invitation to give a talk. I'm also in debt to Roman Bezrukovnikov for his support over the years. I'm grateful to him and Professor Goreski for useful comments and suggestions during the preparation of this talk. Contents. So there's 4 sections: Introduction to Quantization, Categorical Quantization, Applications, and Other Projects. The first section, Introduction to Quantization. What do we mean by quantization? In mathematics, quantization refers to a class of algebraic and analytic problems motivated by trying to construct quantum mechanical systems from classical ones. So the motivation comes from quantization in the sense of physics. In algebra, one is usually interested in deforming a commutative algebra, A0, to a non-commutative algebra, A, over some base, which we usually take to be either the power series algebra, which is denoted K with double brackets H bar, the standard setting for the so-called deformation quantization, or else over the polynomial algebra, notated by K single brackets H bar, over a field K. The input for the quantization problem is the K algebra A0, and the Poisson structure on A0 determines the first order deformation of A0. In this talk, the Poisson structure is always symplectic. In other words, spec of A0 is smooth, and the Poisson bracket is non-degenerate in an appropriate sense. Let us illustrate the notion of quantization, as described above, by the example of quantization of a symplectic affine space. So this next example makes it a little more clear. The basic example is the Weyl algebra. Given a symplectic vector space V, 2 n variables, one constructs a deformation of S of V star, which is called the Weyl algebra, W of V star. It's the quotient of the tensor algebra of V star by the ideal generated by these relations, xy minus yx equals h bar times the bracket of x and y for x and y in V star, where this bracket is the dual symplectic form on V star. If we choose a decomposition of V into a direct sum of Lagrangian subspaces, so V equals L direct sum L star, then this Weyl algebra, W of V star, specializes when h bar equals 1 and becomes D of L, which is a version of the algebra of differential operators on the affine space L. So in D of L, L star becomes the multiplication and L becomes the differentiation. So this is the standard picture of the Weyl algebra. This is the local model for all quantizations considered in this talk. Now for the global picture, differential operators and locality of quantization. More generally, for any algebraic variety y, one can consider its cotangent bundle T star y. The algebra of functions on T star y has a natural deformation to a family whose general member is the algebra of differential operators, D of y on y. If y is not affine, we have to talk about sheaves of differential operators, but the affine picture gives you the same idea. Deformation quantization, which means, as you, from the previous slide, over the power series ring, deformation quantization of a symplectic variety x is local in X. On affine charts, it's the product on the quantized, on affine charts, the product on the quantized algebra is given by a series of bidifferential operators, for example, the Weyl product for the Weyl algebra. This is useful for quantizing non-affine varieties and for local to global techniques, as in Gelfand's formal geometry or Fedosov's quantization. Over the polynomial algebra, however, over K of h bar, this is no longer true. One can localize only in half the directions, for example, on y instead of on T star y. This corresponds to the uncertainty principle in quantum mechanics. However, in positive characteristic, locality is again regained because of the big center of the Weyl algebra. For example, the center of the Weyl algebra in the one-dimensional case that we considered before, D of A1, the algebra in two variables, x and d, is generated by x to the p power and d to the p power. This gives rise to the notion of p curvature of a flat connection and p support of a d module, which is a non-conical version of singular support. You have to ask him.
What's the symplectic variety? With such a thing. Yeah.
Okay. The question of classification of quantizations of a given symplectic variety was studied by De Wilde, Lecomte, Fedosov in the C-infinity context, and by Kontsevich, Bezirkovnikov, Kalidin, Yekutieli in the algebraic context. So in the C-infinity context, quantizations are classified up to non-canonical isomorphism by certain series in H bar with coefficients in de Rham cohomology of the manifold. In the algebraic case, certain cohomological vanishing restrictions are necessary for the quantization to exist. Once these are imposed, we have a similar result to the C-infinity case. So references for quantization in the algebraic context are Yekutieli, twisted deformation quantization of algebraic varieties, Bezirkovnikov and Kalidin, Fedosov quantization in the algebraic context, and Bezirkovnikov, Kalidin, Fedosov quantization in positive characteristic. Next section, categorical quantization. In applications, one is often interested in categories of modules over the quantized algebras rather than the algebras themselves. So it is natural to consider a variant on the notion of quantization, which deals with the deformation of a category, the sheaf of categories locally equivalent to the category of modules over a quantized algebra. In characteristic 0, the picture for the categorical quantization is much cleaner than for the usual formulation. Namely, there's a canonical categorical quantization over the power series for arbitrary symplectic varieties, as well as a classification of all categorical quantizations in terms of the de Rham classes as before, with no restrictions on the variety. This is due to Bezirkovnikov, Kalidin, and Yekutieli. A rough explanation is that the non-canonicity in the algebraic case comes from automorphisms of the Weyl algebra that are the identity modulo H bar, but they are inner, at least on the level of formal neighborhoods, and act trivially on the category of modules. So for the case of positive characteristic, due to the big center of the quantized algebras in characteristic P for invertible H bar, the corresponding categories are certain twists of the undeformed categories of coherent sheaves. For differential operators, it's known that these twists, which are given by GM gerbs, are classes in the Brouwer group H2 of X with coefficients in OX star. These twists are obtained by a natural construction from the canonical 1 form on the cotangent bundle. Thus, for general symplectic varieties in characteristic P, we get canonical quantization category for H bar not equal to 0. In other words, over the ring K of H bar inverse, in the presence of an antiderivative of the symplectic form. So I guess when the symplectic form is exact. In a work in progress, we show that for P greater than 2, the category above extends to all H bar, so over the ring of polynomials. See also Bezirkovnikov-Kalidin, whose setting is a bit different. Moreover, we extend this construction to the case where the base of the quantization is a flat scheme over Z mod P to the n. Further questions related to this are classification of all quantizations locally isomorphic to this one, and generalization of the Azimaya property. This is related to p-adic Hodge theory and results by Vologodsky et al. Here's a picture of the universal base of quantization. We get a theory of quantization for schemes over the formal infinitesimal neighborhood of the following subscheme in A1 z of a half. In other words, spec of z of a half polynomial of h bar, polynomials in h bar. So there's a baseline, which is spec of z of a half, and then at 3 we have A1 of f over f3, and at 5 we have A1 of f5. The baseline is when h bar equals 0. Applications. First, in positive characteristic. Go back.
Picture, but I wasn't sure what I was supposed to deduce from that.
I think it's in it. Sorry.
Quantization would take that it defined over the former neighborhood of the picture, and then it produces a category. So the former neighborhood of the horizontal line corresponds to definition of quantization, and then these vertical lines, they correspond to categorical quantization of characteristic P and mod P to the n, which can be done, which can be for non-formal over A1.
Yeah, sorry, I see.
Okay. Applications. Are we finished with the discussion of two applications of quantization in positive characteristic? One is concerned with geometric Langlands program, and the other is with representation theory of semi-simple Lie algebras. Geometric Langlands. So fix a reductive algebraic group G and a smooth, complete algebraic curve C. The geometric Langlands correspondence is roughly a conjectural equivalence of derived categories of D modules on the moduli space of G bundles on C, and the derived category of quasi-coherent sheaves on the moduli space of Durham LG local systems on C. Here, LG is the Langlands dual group. Originally, geometric Langlands correspondence in the Étal-Schiff version arose from non-abelian generalizations of Artin's reciprocity law, Langlands program, in number theory. Geometric Langlands in the D-module version can be considered as a quantization of the Fourier-Mukai duality between Hitchin integrable systems for G and for the Langlands dual group LG. The Hitchin system is an algebraic integrable system, or Lagrangian fibration, whose generic fibers are abelian varieties. For G equals GLN, a family of Jacobians of proper curves, namely the spectral curves, in the cotangent bundle of C. In order to apply the above theory of quantization to geometric Langlands, we have to work either in the deformation quantization setting or in positive characteristic. The former setting was studied by Arinkin, the characteristic P1 by Bezirkovnikov, Braverman, Groishnig for GLN, Th. Chen, and Zhu for general reductive groups. My thesis deals with the GLN case of quantum geometric Langlands in characteristic P, which is a deformation of the classical one that has twisted D modules on both sides of the equivalence. Also, in a joint paper with Bezirkovnikov, we reprove the Beilinson-Drinfeld theorem on the algebra of global twisted differential operators on Bun-G for G equals GLN using reduction to characteristic P. All the projects listed above, except Groishnig's work, deal with the generic locus of the Hitchin base that for GLN parameterizes smooth spectral curves. Second application to symplectic resolutions. A symplectic resolution is a proper birational map, x to y, from a smooth symplectic variety x to a singular Poisson variety y, often with a contracting GM action, having certain good properties. An example is the Springer resolution of the nilpotent cone of a semisimple Lie algebra G. Its quantization is the quotient of the enveloping algebra U of G by a central character. Many questions in representation theory are reduced to the study of modules over quantized symplectic singular varieties y as above, which, using a derived equivalence result, can be translated to the quantization of x. Jointly with D. Kubrek, we show that in characteristic P, the Brouwer group class coming from the quantization of x descends from x to y. This allows one to pass between x, y, and their quantizations, and is useful for connecting representation theory to geometry by realizing representations of the quantized algebra of functions in positive characteristic as complexes of coherent sheaves. Other projects. I want to conclude by saying that there are other projects I work on, but I couldn't mention in this talk, and describe one of them briefly. Namely, in a joint work with Ginsburg and Dobrovolska, we generalized the geometric interpretation of the Katz polynomial, which counts quiver representations over finite fields, used as a key step in the recent proof of the Katz conjecture by Hausel, Letellier, and Rodriguez-Villegas, and give it a more geometric proof. Thank you for coming.